Report Group 2. Linear Algebra. Loren John Reed. Paron de Jimil. Iragan Rostem. Manlimos Axel J. Vincent Ian Estrada. Eigenvalues and Eigenvectors.
Good afternoon, everyone. Good afternoon, ma'am. The group 2 will discuss the eigenvalues and eigenvectors. So, where can we use eigenvalues first? So we can use eigenvalues to solve system of linear differential equation, describe natural frequencies of vibration, separate motion, distinguish state of energy, and much more. So pre-definition workup. We start by considering the matrix A 2 by 2 and vector x is given below 1 and 1. So first we must solve first the eigenvector before the eigenvalues. So by using scale a times x equals lambda times x. So first a times x, where by performing multiplication 1 times 1, 4 times 1, and then 2 times 1 plus 3 times 1. So it result 5 and 5. So we get the eigenvalues, which is the 5, and the eigenvectors is 1 and 1. So by definition of eigenvalues and eigenvectors, let A be an nx matrix x non-zero and times 1 column vector and lambda as scale if A times x equals lambda times x, then x is an eigenvector of A and lambda or the eigenvalues is an eigenvalues of A. So we use this scale ganiha. So the original equation that we use is the A times x equals lambda times x, and then to continue we must subtract according to the theorem, we must subtract the lambda x from both sides, factor out x, so that it become A times x minus lambda x equals 0. So in between of lambda times x, we will add the identity matrix, but just like multiplying by 1. So in theorem, any invertible matrix only has one solution. Therefore, A minus lambda I needs to not be invertible, and non-invertible matrices all have a determinant of 0. So now we move forward by finding lambda such that determinant close parenthesis A times minus lambda I equals 0. So what are eigenvalues? So given a matrix A and x is the eigenvector and lambda is the corresponding eigenvalues. If a times x and lambda x, it must be square, and the determinant of a minus lambda I must be equal to 0. So factor. So we have close parenthesis a minus lambda I times times x equals 0 if we use the tri trivial solution. So the trivial solution occurs when the determinant is a minus lambda I equals 0.
Example, find the eigenvalues of A that is fine such lambda such that A is equal to lambda 1 equals to 0, 1. Problem, A is equal to matrices 1, 4, 2, 3. A minus lambda 1 equals 1, 2, 4, 3 minus lambda 1, 0, 0, 1 is equals to 1, 4, 2, 3 minus y 0, 0 lambda is equals to y minus lambda 2, 4, 3 minus lambda. Therefore, that A is equal to lambda 1 is equal to matrices 1 is equal minus lambda 4, 2, 3 minus lambda is equal to 1 minus lambda 3 minus lambda is minus 8. The answer is x lambda squared equals to 4 lambda minus 5. Find x such that ax is equal to 5x where problem a is equal to 1, 4, 2, 3. Recall that our algebra from before show that if solution ax is equal to yx, then a minus lambda 1 x equals to 0. Therefore, we need to solve the equation a minus y1 lambda 1 x equals to 0 for x when lambda is equals to 5. A minus 5 1 is equal to 1, 4, 2, 3 minus 5 1, 0, 0, 1 is equals to 4 negative 4, 4, 2, negative 2. Calculating the eigenvectors values. Expand the that a minus lambda I is equal to 0 for a 2 times 2 matrices. That a is equal minus lambda I is equal to that matrices A11 and A12, A21 and A22 minus y 1, 0, 0, 1 is equal to 0. Eigenvalue example. Considered A is equals to matrices 1, 2, 2, 4 lambda squared is minus A11 plus A22 lambda plus A11 A22 minus A12 A21 is equal to 0. Lambda 2 minus 1 plus 4 minus lambda plus 1.4 minus 2.2 equals 0. And the answer is lambda squared is equals to 1 plus 4 y is equals to lambda is equals to 0, comma, lambda is equals to 5. The corresponding eigenvectors can be compounded as lambda is equals to 0, matrices 1, 2, 2, 4 minus 0, 0, 0 times x and y is equals to 0, matrices 1, 2, 2, 4 times x, y equals to 1x plus 2y, 2x plus 4y equals to 0, 0. A lambda is equals to 5, 1 matrices 1, 2, 2, 4 minus 5, 0, 5 times x and y is equals to 0. Matrices negative 4, 2, 2, negative 1 times x and y is equals to negative 4x plus 2y, 2x minus 1y is equals to 0, 0. 4 lambda is equals to 0, 1 possible solution is x is equals to 2 and negative 1. 4 lambda is equals to 5. One possible solution is x is equals to 1 and 2.
Key idea: finding eigenvalues and eigenvectors. Let A be an n by n matrix. To find the eigenvalues of A, compute P open parenthesis lambda the characteristic polynomial of A. Set it equal to 0, then solve for lambda. To find the eigenvectors of A, for its eigenvalues, solve the homogeneous system. Open parenthesis A negative lambda 1 x equals 0. Put another way. Summary: to solve the eigenvalue problem for an n by n matrix, follow this step. Compute the determinants of A negative lambda 1 with lambda subtract along the diagonal. These determinants start with lambda n or negative lambda n. It is a polynomial n lambda of degree n. Find the roots of this polynomial by solving determinants open parenthesis A negative lambda 1 equals 0. The n roots are the n eigenvalues of A. They make A negative lambda 1 singular. For its eigenvalues, lambda solve open parenthesis A negative lambda 1 x equals 0. To find an eigenvector x. Example: find the eigenvalues of A, and for its eigenvalue find an eigenvector where problem A equals close parenthesis negative 3, 15, 3, 9. Solution: determinants open parenthesis A negative lambda sub 1 equals absolute value negative 3 negative lambda 15, 3, 9 equals open parenthesis negative 3 negative lambda open parenthesis 9 negative lambda negative 45 equals lambda sub 2 negative 6 lambda negative 27 negative 45 equals lambda squared negative 6 lambda negative 72 equals open parenthesis lambda negative 12 open parenthesis lambda plus 6. Therefore, determinants open parenthesis A negative lambda 1 equals 0 when lambda equals negative 6 and 12. These are our eigenvalues. Example: find the eigenvalues of A, and for its eigenvalues find an eigenvector where problem A equals open parenthesis negative 3, 15, 3, 9. Solution for lambda sub 1 equals negative 6. We need to solve the equation open parenthesis A negative open parenthesis negative 6 1 x equals 0. To do this, we need to form the appropriate augmented matrix and put it into reduced row echelon form. Open parenthesis 3 15 0 3 15 0 reduced row echelon form close parenthesis 1 5 0 0 0. Our solution is x sub 1 equals negative 5 x sub 2. X sub 2 is free. In vector form, we have x equals x sub 2 close parenthesis negative 5 1. We may pick any non-zero value of x sub 2 to get an eigenvector. A simple option is x sub 2 equals 1. This we have the eigenvector x sub 1 equals close parenthesis negative 5 1. We use the notation x sub 1 to associate this eigenvector with the eigenvalue lambda squared.
My name is Benjamin B. Estrada. Find the eigenvalue of A, and for its eigenvalue find a eigenvalue where problem A equals negative 3, 15, 3, 9. We now repeat this process to find an eigenvector for lambda 2 equals 12 in solving open parenthesis A minus 12 close parenthesis eigenvector equals 0. We find negative 15, 15, 0, 3, negative 3, 0, 1, negative 1, 0, 0, 0. Solution in vector form, we have eigenvector equals x sub 2, 1, 1. Again, we may pick any non-zero value for x sub 2, and so we can choose x sub 2 equals 1. Thus, an eigenvector for lambda 2 is eigenvector 2 equals 1, 1. To summarize, we have eigenvalue lambda 2 equals negative 6 with eigenvector x sub 1 equals negative 5, 1. Eigenvalue lambda 2 equals 12 with eigenvector x sub 2 equals 1, 1. Example, find the eigenvalue, find an eigenvector where A equals 3, negative 3, 15, 3, 9. We should take a moment and check our work. Is it true that a eigenvector 1 equals lambda 1 eigenvector 1? A eigenvector 1 negative 3, 15, 3, 9, negative 5, 1 equals 30, negative 6, open parenthesis negative 6 close parenthesis negative 5, 1. Yes, it appears we have truly found an eigenvector pair for matrix X. For example 1, matrix A has 2 eigenvalue lambda equals 1 and lambda 1/2. Look at determine close parenthesis A minus lambda minus 1/2 close parenthesis. A equals 0.8, 0.3, 2, 0.2, 0.7,
0.8 minus lambda 0.3, 0.2, 0.7 minus lambda equals lambda squared 3 squared lambda plus 1 half equals close parenthesis lambda negative 1 close parenthesis lambda negative 1 2 ay 1 half close parenthesis a minus I open parenthesis a minus I close parenthesis x sub I equals 0 is ax sub I equals x sub I, and the first eigenvector is close parenthesis 0.6, 0.4 close parenthesis open parenthesis open parenthesis a minus 1 half sub I close parenthesis x sub 2 equals 0 is x sub 2 equals 1 half x sub 2, and the second eigenvector is close parenthesis 1 negative 1 open close parenthesis open parenthesis x1 equals 0.6, 0.4 ax sub 1 equals 0.8, 0.3, 0.2, 0.7, 0.6, 0.4 equals ax sub I open parenthesis ax equals x means that lambda 1 equals 1. X sub 2 equals 1, negative 1, and ax sub 2 equals 0.8, 0.3, 0.2, 0.7, 1, 1 equals 0.5, negative 0.5. This is 1 half x sub 2. So lambda 2 equals 1 half. Lambda equals 1. Ax sub 1 equals x sub 1 equals 0.6, 0.4. Lambda equals 0.5. Ax sub 2 equals lambda 2 x sub 2 equals 5 minus 5 x sub 2 and 1 minus 1. Properties of eigenvalue and eigenvector.
Example problem: let A1 0 0 2 4 0 3 5 6 find the eigenvalues of A. To find eigenvalues, we compute that A negative lambda 1 solution that A minus on negative lambda 1 equals 1 negative 1 minus lambda 0 0 2 4 minus lambda 0 3 5 6 negative lambda equals to 1 negative lambda 4 negative lambda and 6 negative lambda. Since our matrix is triangular, the determinant is easy to compute. It is just the product of the diagonal elements. Therefore, we found and factored our characteristic of polynomial very easily, and we see that we have eigenvalues of lambda equals 1, 4, and 6. The eigenvectors and eigenvalues of A and A the power of negative 1. If lambda is an eigenvalue of A, then 1 lambda is an eigenvalue of A raised to the power of negative 1. The corresponding eigenvectors are the same. Why is this the case? Consider an invertible matrix A with eigenvalue lambda and eigenvector x. Then by definition we know that Ax equals lambda x. Now multiplying both sides by a power of raised to power of negative 1. Ax equals lambda x. A negative 1. Ax equal A negative 1 lambda x. Then x equal lambda a raised to power of negative 1 x. And then 1 lambda x equals a raised to power of 1 x. We have just shown that a raised to power of negative 1 x equals 1 and 1 lambda x. This by definition show that x is an eigenvectors of A raised to power negative 1 with eigenvalue 1 and lambda. This explains the result that we saw above. The eigenvectors and eigenvalues of A and A. The eigenvalues of A and A raised of B are the same, but eigenvectors are different. We can answer the eigenvalue question relatively easily. It follows from the properties of the determinant and the transpose. Recall the following two facts. 1. A plus B raised of B equals A raised of B plus B raised of B. Theorem 11. And 2. Det A equal det A raised of B. Theorem 16. We find the eigenvalues of the matrix by computing the characteristic polynomial. That is, we find that A negative lambda 1. What is the characteristics polynomial of A raised of B? Consider that A raised of B negative lambda 1 equals that A raised of B negative lambda 1 raised of B, since 1 equals 1 raised of B equal that A negative lambda 1 raised of B. Theorem 11 equals that A negative lambda 1 theorem 16. So we see that the characteristics polynomial of A raised of B is the same as that for A. Therefore, they have the same eigenvalues. Theorem 19. Properties of eigenvalue and eigenvectors. Let A be an x an n by n invertible matrix, but the following are true. 1. If A is triangular, then the diagonal elements of A are the eigenvalues of A. 2. If lambda is an eigenvalue of A with eigenvector x, then 1 lambda is an eigenvalue of A raised of negative 1 with eigenvector x. 3. If lambda is an eigenvalue of A, then lambda is an eigenvalue of A raised to t. 4. The sum of eigenvalues of A is equal to TRA, the trace of A. 5. The product of eigenvalues of A is equal to that A, the determinant of A. Example problem. Find the eigenvalues and eigenvectors of the matrix A equals 1, 1, 2, 2. To find the eigenvalues, we compute that A negative lambda 1 solution. that A negative lambda 1 equals lambda 1 negative lambda 1 to 2 negative lambda equals 1 negative lambda 2 negative lambda then negative 2 equals lambda raised to power of 2 negative 3 lambda then equals to lambda negative 3. Our eigenvalues are therefore lambda equals 3, 0. For lambda equals 0, we find eigenvectors 1, 1, 2, 2, 0, 0, 0, 0, 2, 1, 0, 2, 0, 0, 0. For lambda 3, we find the eigenvectors negative 2, 1, 2, 1, 0, 0, 2, 1, 0, negative 1, 0, 0. This shows that x sub 1 equals negative 2 x sub 2, and so our eigenvectors x are x equals x sub 2 2 negative 1, and this shows that x sub 1 equals x sub 2 are so our eigenvectors x equal x sub 2 1, 1.
Maraming salamat sa panonood.